Previously, we covered the core foundations. Now in part 3, we tackle how two rival teams proved a black hole sits at our galaxy's center. Part 3, how scientists finally photographed Sagittarius A itself. Handschanten Orbital Dispatch. Script, Nanbond. How two rival teams proved a black hole sits at our galaxy's center. Part 3, how scientists finally photographed Sagittarius A itself. Hook. In the previous episode, we watched the star S2 swing past Sagittarius A close enough to let physicists measure a genuine relativistic redshift, direct evidence that something extraordinarily massive and compact sits at our galaxy's center. But stellar orbits and redshift measurements, however precise, are still indirect. The question this episode answers is simpler and more demanding. Could anyone actually photograph the thing? Intro. Taking a picture of Sagittarius, A sounds almost absurd. It sits 26,000 light-years away. Its shadow, the dark region where light is bent around the event horizon, spans roughly 50 micro-arcseconds across the sky. To resolve something that small, you would need a radio telescope roughly the diameter of the Earth itself. That is, more or less, exactly what the Event Horizon Telescope collaboration built. Section 1. Building an Earth-sized dish. The EHT is not a single instrument. It is a network of 8 radio observatory sites, spread across 4 continents and the South Pole, that observe simultaneously at a wavelength of 1.3 millimeters. Each site records data onto hard drives that are later physically shipped to correlating centers. The technique is called very long baseline interferometry, and in simple terms, it combines the signals from all those distant dishes mathematically so that the effective resolving power matches a dish as wide as the distance between the furthest pair of stations. In this case, that means a virtual telescope roughly the size of our planet. Section 2. Why Sgr A was harder than 87. The EHT released the first ever image of a black hole in 2019, the supermassive object at the center of galaxy M87. Sgr A was always going to be harder, and there's a specific reason why. M8, its black hole, is billions of times the mass of our Sun. Gas orbiting it takes days to weeks to complete a circuit. That means it sits relatively still during an observation. Sgr A is roughly 4 million solar masses. Gas close to it can complete an orbit in minutes. So over the course of a single night's observation, the source is physically changing while you're trying to photograph it. It's like trying to take a sharp portrait of someone who won't stop moving. To handle this, the EHT team developed machine learning algorithms, specifically a technique called regularized maximum likelihood imaging, which tested thousands of possible image reconstructions against the actual measured data and selected the ones that remained consistent across all of them. The result was not one image, but a family of plausible images, from which researchers extracted the common features. A bright, broken ring of emission surrounding a central dark region. Section 3. What the ring actually tells us. That glowing ring isn't the black hole itself. Black holes emit no light. What you're seeing is hot plasma, heated as it falls inward, with its emission gravitationally bent and focused toward us. The dark central region is the shadow cast by the event horizon and the photon sphere around it. And here is why this matters beyond the visual spectacle. The size of that shadow is a direct prediction of general relativity. The EHT team measured it and found it matched the mass already established by 3 decades of stellar orbit work, Genzel and Gez's campaigns, to within the measurement uncertainties. 2 completely independent lines of evidence, using entirely different methods, converging on the same answer. That's about as solid as confirmation gets in observational science. Closer. We went from watching stars trace invisible curves in the infrared to detecting a redshift as a star grazed the horizon, to actually imaging the shadow of the object those stars have been orbiting all along. Each step closed the gap between inference and direct observation. Next episode, Part 4 explores the next key question: what these measurements mean for the physics we still don't fully understand. If this series is useful to you, subscribing helps the channel keep making it. Episode Guide. Part 1. The two rival teams. Part 2. S2's 2018 close pass. Part 3. You're here. The EHT image explained. Part 4. Coming soon. Questions about the imaging process? Drop them below. That is Part 3 of how two rival teams proved a black hole sits at our galaxy's center. In Part 4, we explore the next key question. Subscribe so you do not miss it.